You sure that's worked?
Do you want to check?
We'll find out later.
Alright, cool.
It should work.
Yeah.
Okay, good. Alright.
That's how recording's going to start.
Okay, well, I'll get started now. See, I'll leave the door open a little bit just in case people do come late, but Anyway, welcome to this talk on galaxies. This, obviously, as per usual, I don't take credit for the images and diagrams and stuff that you see in this presentation. I basically report the images and data back in a way that I can explain. This talk will basically take us from the beginning of how galaxies formed a few 100 million years after the Big Bang and to their eventual end in an inconceivably long period of time. It's nice to see so many people here again and quite a lot of familiar faces at this point. So I feel a good place to start is just by saying, our galaxy is actually really big? As simple as that sounds. The main disk of our galaxy spreads 144,000 light years in diameter, and it contains around 150 billion stars. That's big by galactic standards. It's not a tiny galaxy, unlike our sun when we talk about the context of the solar system. But what exactly defines a galaxy? Well, to start with, galaxies are unbelievably diverse. They are so diverse I don't even want to try and start being able to actually classify them. You have the standard types of galaxy, which we will explore during this presentation. But the kind of key things to note are the shape, the structure, even the stars in it are defined by the history of the galaxy itself, from collisions with other galaxies to events that rift deep in their heart. Not all galaxies even have one core, some have multiple. Galaxies tend to be defined by a band of stars and dust and gas orbiting one or more nuclei and being disconnected from very close regions of space. That doesn't mean that something that is orbiting another galaxy isn't still defined as a galaxy. Satellite galaxies are common, especially for large galaxies such as most of these. The Milky Way has several, tens if you consider some of them, and even some of these satellite galaxies are massive. How these structures form is quite interesting because it's not a simple birth and death life cycle, such as stars. These structures grow over unbelievably long periods of time, and there's no predefined destiny made by what mass it is or what it's made from. Everything in a galaxy is quite random compared with anything else that we've looked at in any of these talks so far. To give you an idea of how diverse galaxies are today, you can kind of compare them to the first galaxies. Now, the first galaxies were nothing like the ones you see today. They would have had thousands to a million stars. They are torrid pockets of population-free stars, early, very metal-poor stars, that are birthed from clusters similar to ones we see today, but in much larger numbers. These aggregations of stars simply orbited around themselves in the earliest days. They didn't have a discernible nucleus, not like some of the galaxies, well, most of the galaxies that exist in the contemporary era. Instead, some of the dynamics that played out in early galaxies were completely alien to what we see today. First of all, in some of the larger clusters of these, you would have pockets of denser stars in the middle that have stars then orbiting it, a bit like a super-scaled binary solar system. These stars, though, would live about 1 million years. They fuse extremely quickly, causing very rapid chains of supernovae. This led to a point in time between about 190 million years after the Big Bang and 200 million years, where black holes started popping up at such a rate, it actually disabled the ability of galaxy formation. Until enough stars were able to stabilize orbiting these new cores of black hole masses, no galaxies could really take place. It took an extra 100 million years before the universe was stable enough to allow galaxies to take place in the same kind of form as these early ones that we see through the James Webb Telescope today. Another interesting dynamic is that these stars were so extreme, you could end up with cases of central stars larger than the entire solar system we live in, going supernova and their outer layers remaining intact. You end up with black hole inside a star. That could be the core of a proto-galaxy. As these galaxies develop over time, they gain more mass from surrounding gas clouds and they accumulate their mass through production of stars. The thing that binds them, though, the missing formula in this system, you have all of the mass there that we can see, that we can still see today. But what is the key ingredient that actually allows a galaxy to maintain its own structure? What is the key ingredient that makes it such a vast structure that we see today? The answer to that question comes with missing mass. This is a quote describing the formation of the universe in terms of its constituent parts. The 5% visible baryonic matter, the 68% unimaginable dark energy, that is what's resulting in the expansion of space, which will come up later. But the key we're focusing on today is the 27% undetectable. That is dark matter. And dark matter behaves in a sort of similar way to normal matter. It has mass. But you can define the particles like they are ghost particles. They have a mass that we can detect, but they don't interact with other particles around them in the same way that normal mass would. Because of that ratio, though, the amount of undetectable matter in these systems is so vast, no computer simulation could have ever rendered a galaxy without adding in that extra mass. This missing mass isn't just seen in holding galaxy clusters together, but it's also sometimes seen in phenomena such as the Phoenix cluster. This is a picture of the Phoenix cluster in visible light versus it in X-ray. Phoenix cluster is known for an odd phenomenon that's called X-ray cavity. These are massive pockets of rapidly cooling gas that have been carved out by massive X-ray pulses from its galactic core. When I say massive, they are 600 and something thousand light years long. They are enough to embed 6 Milky Ways in lengthwise. When astronomers found this cluster, they worked out that a staggering amount of the mass to actually make that even remotely possible was just not there at all. Beyond no simulation being able to make it, no one could actually explain what they were even seeing. To give you an example of how much this dominates the formation of galaxies. I have a comparison. Obviously, it's a tradition that I always bring a rock of some kind, but this one's a little bit different. This is iron pyrite. It has a mass, a density of about 5,000 kilograms per meter cubed, which makes it about 5 times denser than water. The equivalency between these two suggests if this was the mass that we can actually see in the visible universe, this is what we can't see. And when you hold it combined, it does go to show how big a difference that actually is. It just worked that way around. Now, this isn't just resulting in galaxy clusters and chains that we can't comprehend, but it's also creating the galaxies themselves. In this image, you can see a phenomenon called gravitational lensing, where the galaxy cluster is so massive it's actually bending space to the point where light bends around it. That is a phenomenon not possible without adding dark matter into the picture. These are all byproduct truths. They all say there is this missing mass. It is insane how much more of it there is in visible matter. But they're not helping us understand what it actually does. Obviously, it holds the galaxy together. But how does that affect the dynamics? How does that affect what a galaxy actually looks like? Dark matter's role is a really interesting one, because it actually stretches even to the structure of galaxies we take for granted. This is the Phantom Galaxy, a rare version of a grand design spiral galaxy, one that has all of its rings perfectly intact. That has taken an infrared to see the spiral arms at their best, because it works best for this description. The way that those arms wrap around themselves is due to the propagation of pressure waves throughout the galaxy over its lifetime. As they move out and the galaxy itself rotates, it creates different bands of these spiral arms. But if galaxies moved in the way that we would predict based on every other known law of physics without dark matter in the picture, that would not be how it looks. Take, for example, the Earth orbiting the Sun. We orbit in a year. Neptune, significantly further out, so is it 30 or 40 astronomical units or something like that, is much more than that proportionally slower orbiting. The pattern seen in galaxies, especially spiral galaxies, is not the same. You get very fast movement around the core, creating something that can be analogous to almost like a solar system, but of a million stars. But then further out, they start to slow down, as you would expect. As you reach the periphery, however, the stars speed up their orbit. By extreme magnitudes, on some galaxies it's found that the stars on the periphery are orbiting 20 times faster than they're supposed to be. This phenomenon isn't so much just to do with the fact that dark matter is presumed in there and binding the structure together, but it is instead the fact that the shape of dark matter itself creates a sort of halo-like donut, essentially, around the edge of the galaxy. This is called the dark matter torus. And the idea is it provides the extra mass you need to make galaxy clusters like this stay together in simulations. But it also provides the answer to why the stars on the periphery are being dragged along at such insane speeds. If you think of this dark matter, because it's weakly interacting, forming a gravitational pull evenly around the edge of a galaxy, not only you have it holding together the structure of the galaxy, but you have it evenly pulling at every point forwards along the edge, rapidly speeding up star rotation rates around the core. Now, this accounts for so much that it has to be either a notable factor where the theory is sort of right, or that the theory is exactly right. And obviously, once you actually try the comparison between the visible mass and the missing mass, it is quite extreme, the difference. So back to the formation of the early galaxies now. Going back to the first black holes. Black holes today form the skeleton, the backbone of most galaxies. The ones that you find at the centre are considered supermassive. Those giants like M87 star, 6.5 billion times as heavy as our Sun. These are so fundamental in our understanding of large galaxies today. But they weren't always there. Now, like I was saying earlier, the rate that these cropped up in the early universe with population-3 stars dying so quickly was extreme. But until they could coalesce into one object at the middle of the galaxy, you didn't really have much going for a structure. An example of these kind of solo black holes is one that has actually been found orbiting a blue supergiant, it's called stellar mass because it's within the range of one star collapsing to form it. About 21.1 solar masses in this case. The early universe would have been absolutely dominated by these to the point where it would have just pretty much destroyed the structure of any galaxy trying to form. This makes the next step absolutely crucial. Collisions are what drive a galaxy's evolution, beyond any other force. Black holes have an accretion limit. It's called the Eddington limit. It basically means that if a black hole starts trying to consume enough energy to grow at the rate that we see today, it would emit so much light and radiation it would blast out all of the gas from its local area and basically stop its own growth. Now, presuming black holes stay within this limit, they can grow slowly over time, but nothing compared to when they collide. This is a nice image of two intermediate-sized galaxies colliding, and this is the kind of catalyst that would have driven early galaxy evolution. Galactic mergers were extremely common in the early universe, and each of these dust-ups would have left the new galaxy enriched with new elements and also put pressure on stars to form. As I've mentioned in one of my previous talks about star formation, stars can have all of the right ingredients to exist. The mass, the dust, the metals, etc. But unless they're acted on by angular momentum, they will never collapse into their core. These kind of processes are what create those mechanisms on the largest scale. They can take a galaxy that would produce about a solar mass a year, like the Milky Way, to boost it to 1,000 or 2,000 solar masses a year. The downside is, sometimes a lot of the stars and gas are lost, depending on how these galaxies collide. Interestingly, when they collide in a way that is detrimental to the structure of the galaxy, they're often known as a puffball, because that is what they essentially look like. You end up with things escaping from every single angle into stellar space. These collisions also feed the black holes at the heart of the galaxies. When the black hole is interacting with a large portion of matter around the core, it is known as an active galactic nuclei. These active galactic nuclei can, in some cases, be the most luminous sources in the entire universe. There are these objects known as quasars, which are visible from 10 billion years look-back time, which is now about 30-odd billion light-years in real distance, that are still so bright, some of them are mistaken to be stars within the bounds of our nearby galaxies. These quasars are created by interactions in the inflowing matter within the accretion disk of a black hole itself. This creates an unbelievable amount of luminosity. These active galactic nuclei can blast out unbelievable amounts of gamma rays and X-rays, which obviously has a detrimental effect if any life was to try and form there. There are many examples of these kind of active galactic nuclei in the early stages of the universe, before about 10 billion years ago. But the Hubble Deep Field, a legendary image for its time, most of the distant backdrop images you can see of that, almost all of them are these active galactic nuclei. They're the only ones that can shine through that larger distance. None of these events would really be possible without galactic mergers. There is the second force going on there, the 68% that I mentioned earlier. This is dark energy. Dark energy has been playing a game of its own since pretty much the formation of the universe, though the rate of its effect accelerates over time. This is the force between galaxies in intergalactic space, stretching apart space itself. For this, you can imagine plotting some dots on the surface of a balloon before you blow it up. When you blow it up, all of those dots appear to move away from each other at increasing speeds, when all they are doing is moving through the dimension perpendicular to themselves. That dimension in this case is time. The universe inflates like that balloon on all scales. That means that all of these pockets that were once close by galaxies when they were forming suddenly get pulled apart with giant voids in between them, creating a structure known as the cosmic web. The cosmic web is crucial for understanding everything that happens past a certain point in the universe's evolution, because this is fundamentally what defines where galaxies end up. Without this force pulling galaxies apart, what do we think would happen? They would all collapse. Now, Einstein was the first to posit that this was an issue. But when he proposed this, he provided something to suggest the universe was stationary. He created a value that fought back against gravity, as this one sort of seems to do, but in a way that made the universe stationary. When it was proven that the universe wasn't stationary, he accepted that to his grave as his greatest blunder. Yet here we are. This force is influential in why galaxies don't evolve eternally. Every galaxy will end at some point. As these voids grow, so does the space between them, obviously. Intergalactic space. Intergalactic space is as empty as the universe gets. Even in the upper atmosphere, well, beyond the upper atmosphere, you can still have several million to billions of atoms per cubic meter. In intergalactic space, generally you have about 1 per cubic meter. That is orders of magnitude lower than you would ever achieve inside our own solar system. Yet, despite this low density, the sheer size of these voids mean that there is actually probably more matter in the space between galaxies than there is in all galaxies combined. Now, obviously, like I said before, stars to form need that crucial interaction of the materials to build them and angular momentum from some nearby event. But there are interesting circumstances. One is ejected rogue planets. Rogue planets are planets that have been stripped of their star by some means. Some of them that are particularly large can actually form on their own without a star. These, especially in galactic collisions, get drawn out from their solar systems as stars pass between one another. And they can get slingshotted out at unbelievable speeds, way beyond their escape velocity for their galaxy. And they can end up in the coldest, darkest void that can exist in the universe. But stars can actually form here, often as a byproduct of interruptions from those galactic collisions. There are few, but possible examples of intergalactic stars that have formed in intergalactic space and captured rogue planets. It is a possibility. So even beyond the light of any nearby galaxy, solar systems are technically possible. Not plausible, but possible. Now, this takes us to the modern era of galaxies, where galaxies have now had 13.8 billion years, well, 13.6 billion years, to diversify, grow, change, and develop, leading to genuinely incredible diversity. These are some of the kind of key types of galaxies, ignoring their extremely long-winded descriptions. So, starting with M87, which is a particularly interesting galaxy because of its radio effects. That jet that you see is actually taken in optical. That's something that is interesting because of its polar jets. Most of the effects you see from those kind of radio galaxies are when they are taken in false colour, but that is an image from optical. M87 itself has a disk diameter of about 136,000 light years, give or take 30,000 light years more than the Milky Way's. But its extended disk goes out to about 490,000. It is immense. It holds several trillion stars. So it's several times larger than Andromeda, which is our largest galaxy that is close to us. And that jet is pretty much visible from the nearest few billion light years. It is a type of galaxy called elliptical. Elliptical galaxies don't exhibit the same sort of structure as spiral galaxies. They have no order. They've been collided with so many times, they basically have stars orbiting in every single plane in every single direction. Depending on what happens to M87 in the near future, it might stabilize into a different kind of galaxy, but that remains to be seen. The Pinwheel Galaxy is immense for a spiral galaxy. It holds around 1 trillion stars, and the spiral arms are preserved through billions of years of collisions, the same as every other galaxy in this local area has endured. The next kind of galaxy is an odd one, because lenticular galaxy is a class of galaxy, but it doesn't really describe much about the galaxy itself. Lenticular means that it's side on with Earth, which the Spindle Galaxy is most notable for because of its angle compared with us. The notation in this case is particularly interesting because it suggests that it is a spiral galaxy. It is actually a very similar galaxy to the Milky Way, but the denotion is it's side on, so therefore it's lenticular. Not all galaxies follow these neat lines to make them the kind of structures we'd recognise them. A good example of this is one called Hoag's object, which you can see from the outset as a particularly weird one. This is a formation of about 8 billion stars, very small, but the outer ring is mostly young blue stars that are recently formed, and the inner bit is older aging stars that make up its core. There isn't really a known reason why that exists, but it's given its own classification as a ring galaxy anyway. The other two demonstrate ones that don't follow any trend. both irregular galaxies. The one of particular note is this one. This is one, like I was talking about at the beginning, that actually has two cores to it. This galaxy is so irregular and weird, with its 30-odd million stars, it is actually tearing itself apart. This galaxy will cease to exist within the next billion years. The counteracting forces from its core are causing so much what's actually called evaporation that the galaxy is basically diffusing itself into space. These are just the main types of galaxies. Obviously, you go in beyond this and you can get very specific, very weird, different ones. But give or take, anything you find will fall into one of these sets. The most interesting for me, though, are the giants. Some of these tend to defy logic in how large they are. So, Alcyonius was classed for a very long time as the largest galaxy ever known. The radio jets seen in that image stretch 6 million light years. That is more than 1.5 times the distance between us and our closest galaxy. The galaxy itself contains some 50 trillion stars, somewhere around 500 times what the Milky Way contains. It is unbelievably powerful in the past, but its current core is made up of one just 400 million solar mass black hole. It is an interesting anomaly of different factors, potentially an unsolved mystery. IC1101, however, is the undisputed largest galaxy. If you put this galaxy, between us and Andromeda, it would stretch the entire distance just with its galactic disk. It is 40 times the diameter of the Milky Way and contains over 100 trillion stars. It is hard to get around the sheer size of that kind of supergiant elliptical. These are potentially the kind of galaxies, not so much Alcyonius because it's an active galaxy, but IC1101 is an interesting question for the Fermi paradox. How many stars do you need to cram into such a small space before contact with an intelligent civilization is inevitable? Potentially, one massive galaxy with 1,000 times as many stars as us. As time goes on, galactic collisions become rarer, but much, much more profound. This is a collection of Hubble images of galactic mergers that are going on with similar galaxies to the Milky Way. And over time, these will keep rejuvenating the life in what's left of the galaxies. Despite this, they will keep losing mass every single time they do this cycle. And eventually, because space is still spreading apart, they'll be blasted so far away from their closest neighbours that it is only the gravitationally bound next door neighbours and the satellites that will be able to even collide. Once they collide, the galaxy will be inert. It won't be able to produce any data. This aging globular cluster shows where that kind of chain is headed. All of these stars are born at the same time. They're all aging at the same sort of rate. They're all dying and slowly turning red. In a few billion years, systems such as this one will grow extremely dark and dim. That is what is in store for galaxies as a whole. It is the long-lived tiny red dwarfs and brown dwarfs that will continue this chain going on for the next 100 trillion years. Within the next 100 billion, the last of the giant stars will pass, with potential exceptions for the fact that black holes, as they become ever more ravenous, once they pass that Eddington accretion limit, it is actually possible for them to create stars. As a black hole takes in enough matter with enough radiation pouring off it, it can create similar gas cooling fractal conditions to the large stars actually being born in the first place. So it is quite probable the last batch of larger stars will be created by the black holes devouring their own galaxy. On the most part, though, galaxies will start to grow dim, and within about 100 trillion years, they will pretty much cease to give off any light at all. The Milky Way isn't safe from this same threat. You may or may not know, our closest galaxy, currently lying at 4 million light years away, Andromeda, is coming towards us at about 220 kilometers a second. In about 3 billion years, it will make contact with the Milky Way and will undergo a series of elongated infalls as it collides head-on several times until the cores eventually merge. This won't be the last collision the Milky Way ever undergoes, but it will be the most major one. The Milky Way is already far enough away from any other cluster of galaxies that our local group of the Andromeda Galaxy, the Triangulum Galaxy, and our respective satellites are all of the mass our group is ever going to get. In about 10 billion years, once this has gone full circle, the Milky Way will start to grow cold, just as the other galaxies will. And unlike before, there'll be nothing to keep feeding into it. By that point, it will contain around 1.3 trillion stars, and it will have gone the full length of its own life cycle. It will potentially become another spiral galaxy again, one that has been colloquially named Milkomeda. And potentially life could continue going on even after this, with the red dwarfs left in our galaxy. But most likely we will not ever see this, because after about 3 billion years the sun will engulf Earth anyway. As things keep moving further away from each other throughout the course of the rest of the universe's life, not only will these galaxies consume all of their local group, but they will be cast so far from their nearest neighbour that they will be faint specks only visible with the deepest field telescopes. As the galaxies slowly fade out, the last remnants would be things like cooling neutron stars, the weakest stars that have been clinging on for trillions of years, and then endless charred remains in the form of black dwarfs. Once they finally fade out, the black hole at the centre will continue to consume most of the rest of the galaxy, conceivably ending up weighing more than the Milky Way does today. At that point, the galaxy will have finally come to an end. Thank you. Questions?
Rogue planets and rogue stars in intergalactic space. How do they get there?
So, rogue planets, because they're quite light, irrespective of other things, they can be. So, during a collision, as was mentioned at the beginning, because of the space between stars, it's very unlikely two stars will ever collide. But stars will pass through other stars' solar systems. That means that, very similar to the talk I had on the solar system, simply the movement of Jupiter within its own path was enough to stir up the entire solar system. So a star coming through the plane of another solar system is enough to slingshot even a gas giant out at over 1,000 kilometers a second. They can then just race off without, well escaping the galaxy's escape velocity and pretty much get lost completely in the dark. If they get captured while they're still in the galaxy, then they have a chance at becoming, trapped again, which is actually what happened to the oldest known planet, Methuselah. So that's been dislodged from its solar system 3 times and now orbits 2 dead stars. It is possible, but some of them will just be banished into deep space.
If they start to fizzle out, is there gravity enough to keep them together? Such a there's only one atom per cubic meter. It's going to be not a lot going on.
Yeah, no, I mean the gravity would keep the thing together. It's the fact that because there's no temperature, every process of cooling is sped up. So you think of ambient temperatures in the solar system when you've got the crust of planets and whatever still being heated to several hundred Kelvin. Even Mars then still froze to its core eventually. The thing is that these planets, when they're dealing with just the background space temperature of 3.7 Kelvin, they get as cold as a planet can be. Their atmospheres freeze solid. Their cores will be completely shut down. They'll have no magnetic field. They will pretty much become like a dead star. It's not so much that they would disappear, just the chance of anything ever happening on them again goes away.
If it's a gas giant, then wouldn't the gas need to be hot in order to be gas? It's cooled down.
Yeah, but it would still cool over time. No, not entirely. It would technically make it nice cold. But only after a really long period of time. Gas giants could technically maintain their own temperature depending on their mass. There's something called the jumbo phenomenon, which is Jupiter mass binary objects. They can form by compressing gas clouds without a star system, because they're essentially closer to failed stars than they are planets. They, because of that phenomenon, can actually maintain heat between themselves for a very long period of time.
So with these intergalactic planets, right? So they're floating through space where there's 1 atom per cubic meter. Are they scooping those atoms up technically? Are they growing in the process?
I mean, anything is growing. But if you compare that to our solar system, you can see how, pointless that is. I mean, Avogadro's constant is times 10 to the 29, I think. I'm not 100% sure, I've not done chemistry in a while. But it's in that sort of order of magnitude. So when you're talking about the difference between a few million and 1, it's still, you're talking less than 20, more than 20 orders of magnitude down from what is conceivably matter.
If the star is alive and the planets back to orbit, can the star join the solar system?
It can, so you can end up with a combination of either transient binaries or stable binaries. Stable binaries are very unlikely from galactic collisions, purely because the angles that they come in are extremely acute, so they've already got their own momentum. For 2 stars, especially if they're similar in mass, overcoming that momentum is a really awkward thing to do. If you have a star like, I don't know, Wolf-Rayet or Class O supergiant or something, one where you're talking about 100 solar masses, then that star will have enough mass to basically capture the star in the solar system that's passing through and grab the entire solar system and drag it with it. So it transfers its momentum to the rest of the solar system and the star itself. That's sometimes less chaotic than this normal event, but it is more interesting. But then you can end up with some interesting binaries. That's probably what happened with this system, or at least some time that it happened with, because the disparity between the black hole itself and the star it's orbiting suggests that there was some kind of interchange between those stars at some point. That's probably not the position that those stars actually evolved in, and their ages probably don't line up very well either. So potentially they could have merged, but they would have merged from within the galaxy instead of two different ones.
That happens with
I mean, yeah, potentially. So it would across the Milky Way. When Andromeda collides, the sun will already be going asymptotic during branch, which would basically mean it's pretty much dead anyway. If it formed a new star, though, after a long period of time, it would be forming a new star in that new galaxy, and potentially that could get entangled with a star that wasn't originally in the Milky Way.
What's the star notation on certain black holes mean? What does the asterisk notation on certain black holes mean?
So M87 star means the black hole at the centre of M87.
Yeah.
Some black holes are given their own name. A lot of them aren't. So when you see M87 star or Phoenix A star or something like that, that means that it's the supermassive black hole at the centre of that galaxy. If it's Cygnus X1 or something like that, then you end up with the fact that that specific black hole has been named itself. Anything else?
I didn't make the slides will be available after.
I mean, we've got it recorded, so that'll be hopefully sorted. We'll see. If not, it's an easy thing to post up anyway. So if you wanted me to make it available, I can literally just make the slides available. So okay. Yep, all good. Okay. Well, thank you for listening, and I hope you enjoyed it.